We have seen resistors being connected in series and parallel and more complicated versions of things. Capacitors can also be connected in this manner. So we can have it in series, parallel, and further complicated things as well. So in resistors, two resistors are said to be in series if they share one common node, right? Or if the same current flows through, or the voltage will add up to the total voltage at this end. So many ways of defining it. Similarly, we have two capacitors in series with the same set of conditions, like V1 plus V2 is equal to total voltage at the ends, and charges. When it comes to charges, if there's a Q over here, this is minus Q, and this will be plus Q, and this will be minus Q. So as a definition, two capacitors are said to be in series when the positive plate of first capacitor is connected to the negative plate of the second. Now, in resistors, we saw equivalent resistance, right? Here too, we are looking at something called as equivalent capacitance. Equivalent capacitor is a single capacitor that can replace the entire combination. Basically, it's that. Now, let's look into derivation. So we're considering three capacitors to begin with. So the capacitance is C1, C2, C, so on and so forth, that are connected in series. And a potential difference V is applied across the combination, right? Something like this. Now, because of the battery source and all of that, we have plus Q and minus Q that will sit on these plates. So by default, induction and all of that, this will be minus Q, this will be plus Q. And with the same reason, this is minus Q and this is plus Q. And the voltage here, if it's V1, V2, V3, those will be equal to V. Okay, guys. So observe in figure that when voltage is applied, opposite charge of magnitude Q moves to either end of the initial uncharged capacitor combination. Due to the conservation of charges, so this is a keyword, equal magnitude charges must form on the plate of the individual capacitor, as the charge is mere being separated within the initial neutral devices. So all these are neutral. We're just pulling and pushing the charges. So this is a very important set of statement that we need to make. Now, in series, total voltage is a sum of individual voltage. So we know that V is equal to Q by C. Sorry, what am I doing? So what I'm trying to tell is V is equal to V1 plus V2 plus V3, right? Now let's substitute V, which is equal to Q by C. So this will be V by CS, which is equal to V by C1, my bad, not V, Q, plus Q by C2 plus Q by C3, where CS is equivalent capacitance for series combination. So we have all of this to be 1, 1, 1, and 1. So we have 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Right? That's it. That's your result. So conclusion is that the reciprocal of the equivalent resistance, capacitance is equal to sum of reciprocal of individual capacitance. We have seen this. Not with resistors, similar stuff. The equivalent capacitance is smaller than the smallest individual capacitor. Again, we can relate it with resistance. The charge on each capacitor will be the same. right? I hope I made sense over here. The potential difference across any capacitor is inversely proportional to its capacitance. Now, for the sake of remembrance, it's like replacing this with a single capacitor wherein D is going to be at a huge distance. So larger plate separated indicates smaller capacitance. Large plate separation indicating smaller capacitance. So you have to remember that when you connect it in series, the capacitance of the capacitor reduces the entire combination. Okay, that's how you can remember. So let me explain it again. Series and parallel combination of things you guys already know of. So we are connecting capacitors in series. So this will be so for any number of capacitor actually. You know. So 1 sorry, 1 by C4, 1 by C5, 1 by C4, 1 by C6, so on and so forth. So voltage drop between them will be V1, V2, V3 and so on and so forth. Here the main thing that you need to understand is that we have a source of charges. So from here we'll have Q and here we'll have minus Q. And because of, right, all this inductance and all of that, so basically charges will attract each other, is it not? So plus Q will attract minus Q. And this in turn will push plus Q over here. And from here you have minus Q and that in turn will create plus Q, so on and so forth. So they will equalize each other. They were initially neutral, so the number of charges will not differ. This is the key point, right? That's why I've written it off so that I don't make any mistake in this. And post that, it's a simple substitution and all of that, and you are done. Okay guys, so you can pause and have a look.